Hi everyone, welcome to the channel. In this video we're going to be looking at another application of differentiation, and that is optimization. And we're going to do it you're looking at an example. So we have an example here. It says a manufacturer needs to make a cylindrical can that will hold 1.5 liters of liquid. Determine the dimensions of the can that will minimize the amount of material used in its construction, which makes sense because manufacturers generally want to spend as little as possible within reason, right, without affecting efficiency or anything like that. So that's why if they use the minimum amount of material, it means they can keep their costs down. So let's see. So let's break this down. The manufacturer needs to make a cylindrical can. So if we look at a cylindrical can, you're looking at something that looks like this. Like that, right? So I'm going to assume, they don't say, but I'm going to assume that it's closed on the top and the bottom, right? So all the material that makes up the can is going to be the top piece, which is a circle, the bottom piece, circle, which is the same size, and then the walls of the cylinder, right? Which if you fold it out, right, if you take it and you fold the can out like that and make it flat, you're going to have one big rectangular piece, right? You'll have a rectangle piece. We need to do that because we're looking at how much material is used in its construction. So it'll be the outside of the can, right? So it's the area of all of this. So we're looking at the area of that one plus that one plus the area of all of that, right? That's what we want to minimize. And whenever they say minimize, right, it means you have to find the derivative of something, because where you have a minimum or a maximum value, the derivative is always zero, right? Whether you're doing optimization or you're doing curve sketching, your derivative is always going to be zero at minimum or maximum. Okay, then it also says that it will hold 1.5 liters of liquid, right? So let's write that down here. So that's the volume, right? The total volume is going to be 1,5 liters, and I'm going to convert that into centimeters cubed, right? Because I want to find my dimensions in centimeters. And that is going to be 1,500 cubic centimeters. Okay, the other thing you know about volume, right, is that there's a formula for that, right? This formula is going to be the area of the base times your height. So the area of your base, because it's a circle, is going to be pi r squared times the height. And I'm making this piece over here. That is the height of the can, right? So if I write it over here, that over there is going to be my height. The radius is going to be there to there. That's r. And it will be the same for both of them. So for that would be r, right? And that illustrates, well, let's make that more in the center. Close that one up. So from there to there is r. And it would be the same the top and the bottom, right? Because that bottom is a circle, and that is also going to be r. Okay, so let me just get myself out of the way here again so you can see what I've written. Right, so you see there, I've written down the formula of the volume, right? Because maybe at some point we're going to need this. They always give you the information for a reason, right? And whenever you start off, especially with word problems, you always write down what you know. Because whenever solving a problem, whether it be an engineering problem or a maths problem, you move from what you know to what you don't know. Okay, so we have volume, that's what they say. We have to look for dimensions that will minimize the amount of material, and as we said, that is going to be area, right? So that means that the area, the total area, let's put here total area of the can is going to be the top right? So let's say that's the top plus the area of your base, plus the walls, right? And that is going to be the walls. Okay, so then the top is a circle, so that is going to be pi r squared. Pi r squared. Your base is also going to be pi r squared. R squared plus your walls. In this case, this is a rectangle, so it's going to be length times breadth, or length times height. And this length here, you will see, comes from the circular part of the can when it's folded, which means it's just the circumference of the base and the top. So I'll put here is going to be, so circumference is 2 pi r times height, right? Okay, and that, let me just show you where that comes from. So this piece here, that piece there, we color it in yellow, right, is the same as this edge over there, right? The bottom bit, that there, that piece is the same as the edge of the base, right? And these two are the same size because it's a straight cylinder. Okay, so if I look at this shape, that's a circle, right? So the edge is just going to be the circumference, and that's where 2 pi r comes from. And the height is just the length or the height of the cylinder. Okay. Now, if we look at what we've got, right? At some point, we are going to want to find the derivative, right? But what you've got here is you've got two different variables. And always, if you can, you want to avoid doing partial differentiation, right? You always want to make your problem as easy as possible. You don't want to do things complicated, right? Always try and make it easy. So the area, I'm going to call it A, equals area. If you look at the variables that you've got here, pi is not a variable. Pi is it's a constant number, right? R, you've got R and you've got H, right? You don't know what those are. But you do know this information here, right? You know that your volume is equal to this formula, and that formula has to be equal to 1,500 cubic centimeters. Okay, 1,500. Okay, we can make this formula in terms of just one variable, so we can relate these two. And I'm going to choose H, and the reason for that is because H is to the power 1. And I'm going to say H is equal to that over pi r squared. Okay, so you see, if you take this H and you substitute it in here, you will then only have one variable. So we'll do that is the same as 2 pi r times 1,500 over pi r squared. Okay, so that is going to be 2 pi r squared plus, what's it, 3,000 over r. Over r. Okay, and that is going to be my A. So now I have an expression for the area, but I want to minimize that area, which means I need to find the derivative of the area. And I'm going to find the A, and my variable in this case is r. So the derivative of this is going to be 4 pi r. Okay, that is the same as, let's just write it here. This is the same as 3,000 r to the minus 1. Right? So the derivative is going to be minus 3,000 r to the minus 2. And because I'm looking for the minimum value or maximum, that has to be equal to 0. Right? So now you can solve for r. So we've got 4 pi r equals 3000 over r cubed. I cross multiply, I get 4. So, and then I cross multiply, I get 4 pi r. Oh, that must be squared, not cubed. That must be squared, right? I was hasty thinking about the next line. That equals to 3000. And if you find r, you're going to get is the cube 3000 over 4 pi, and that works out to 6,2 centimeters. Okay. Right. So now you have a value for r, but you need to ask yourself, is this in fact a minimum value or is it a maximum value, right? And we know that a value is minimum if your second derivative, so if d squared a dr squared is going to be greater than 0 for r equals 6,2, right? And we can check. So our second derivative is going to be, it's going to be 4 pi plus 6,000 r to the minus 3, right? And that's going to be 4 pi, sorry, that's just over 1. I don't know why I put that there. 6,000 over r cubed. If we substitute 6.2 in here, you will find that that is going to be greater than 0, right? Which means you've got a plus sign, smiley face, which means it is in fact minimum. Okay. So the radius r equals to 6.2 is minimum. So now we need to find out what is our height going to be. And that we just substitute into the previous equation that we had. And what was that? That was 1500 over pi r squared. So 1500 over pi r squared, and that's going to be 1500 over pi times 6,2 squared, and that works out to about 12,42 centimeters. Okay, so therefore your dimensions are the radius of the can equals to 6,2 centimeters and the height equals to 12,42 centimeters. Okay, and that's it. All there is to it. And all of the optimization problems work more or less the same. The most important things to remember is that first, read through your word problem, write down what you know, and from what you know, figure out what you need to calculate, and then see if you can use what you know into finding what you don't know. Sounds simple, but it's often not, right? It's just all about practice. Well, I hope you find that video useful, and hopefully I will see you next time. Bye.